Hey guys, welcome to our Friday YouTube lecture. So we'd finished with my daughter on Wednesday looking at these orbitals which build up into subshells, which then build up into shells, these layers of electrons as we move further away from the nucleus, like floors of an apartment building with people in them, except it's now floors and apartments and rooms with electrons living there. And we have in the very first shell of any atom, the 1s subshell, which is made up of a single orbital, as we said. And in every layer, every shell, we see an s subshell. And we give it a number which matches the shell it's in. So if we're in the third shell, we see the 3s subshell. And with every layer that we move to, we see a new kind of subshell appear. So in the second shell, the P subshell makes its first appearance, so we call it the 2P. And in the third shell, although a little bit late, we see the D subshell make an appearance, we call it the 3D. But the layers are bleeding into each other a little bit, and we actually put electrons into the 4s, which is part of the fourth shell, before we then double back and put electrons into the 3D. This makes things a little bit more complicated, certainly in terms of remembering the order of the subshells. Say that 5 times fast. But there's actually a neat little trick we can use to remember the order of the subshells that we'll talk about. First, let's look at putting electrons into the shells of an atom, and we follow just 3 basic principles. First is put the electrons into the lowest energy subshells first. And this is what we sometimes call the build-up principle or Aufbau principle. Start at the bottom on the ground state or the ground floor of the apartment and fill up the apartments in the building from the ground up. Fill up the electrons in the shells from the ground state up. Our second rule is that each individual orbital can only hold a maximum of 2 electrons. And so this is what we call the Pauli exclusion principle. It's like each bedroom in an apartment block had a maximum of 2 occupants. And then finally, Hund's rule, and this is only for subshells when there are orbitals of equal energy. So that either we're talking about one of the P subshells or talking about a D subshell, which have multiple orbitals. Let me get my pen working for this. When we've got orbitals of equal energy, part of the same subshell, the first electron comes in, and let me use the 2p here. So we'll assume that the 1s and 2s have been filled first. When we come to the 2p, first electron moves in. By the way, if we haven't already mentioned this, we draw the electron as a half-headed arrow. And when the second electron for this subshell comes along, he doesn't have to share. He's got his own separate empty orbital next door. So he moves in there. And then the third electron, again, he moves in there. So when we have orbitals of equal energy, the subshell half fills before we start to see the electrons fill the subshell completely. Because of course, Aufbau principle, fill the lowest energy orbitals and subshells first. So although the electrons don't like living in the same orbital, and therefore they take advantage of the other orbitals in a D or a P subshell, they'd rather share than move up to that higher energy level. So they're lazy and antisocial, meaning they don't want to move up to a higher level, the lazy part, and they're antisocial because they don't want to share, but they're more lazy than antisocial, so they will share if they have to. Okay, so those 3 guiding principles let us know where the electrons are for any atom. And so if we look at neon, if we look at the periodic table, is the 10th element in the periodic table. There we go, neon right there. And so that means it has 10 protons, but it also means that it has 10 electrons when electrically neutral. And so as we put those electrons in, Aufbau principle, fill the lowest energy subshells first, so 1 and 2. Then Pauli exclusion principle tells us that 2 is the limit, so the third electron goes in there, and then the fourth goes in there. Pauli exclusion principle again tells us we have to move up to the next orbital, which is in the next subshell. So 1, 2, 3 electrons go in, following Hund's rule. It tells us that we don't pair up when there's empty orbitals of the same energy. And then the 8th, 9th, and 10th electrons go in there. So we've completed the second shell just as we have reached the end of the second row of the periodic table. That's not a coincidence. If we look at argon, which is the next example we have to do, and we can clear this and move across the page to the diagram for argon that we've got in our notes. Do remember, if you're coming to campus for class, for lecture, you get access to these notes and can make a copy. So with argon, it's the 18th element, so we're talking about 18 electrons when electrically neutral. Of course, 1 and 2 in there, following Aufbau principle. Pauli exclusion tells us that 3 and 4 are there. And then Aufbau tells us to move up to the next lowest energy subshell again. So 5, 6, and 7 following Hund's rule. Then 8, 9, and 10, that's where we were for neon. And then 11 and 12, as Pauli exclusion principle tells us we've run out of room. And then 13, 14, 15 go there according to Hund's rule again. And then 16, 17, 18. We complete that third layer just as we complete counting boxes in the third row of the periodic table. There we go. Again, this isn't a coincidence that we've reached this point. It's because Mendeleev created the periodic table based on the relative chemical reactivity of the elements. That chemical reactivity plays a large part due to the arrangement of electrons in the shell. So we can summarize this by saying that every time we count boxes around the table, we're counting electrons in the shells. And specifically, every period, every row that we're counting boxes in, that's counting electrons in that particular shell. And we can see that if we look at the periodic table again. Of course, the first shell we said just has the 1s subshell, which has a capacity for 2 electrons, like we have 1, 2 elements in the first row of the table. In the second shell, we've got the 2p and the 2s subshells with 6 and 2 electrons, 8, and we've got 1, 2, 3, 4, 5, 6, 7, 8 boxes in the second row. Third row, we see initially the S and P again, giving us another 8 elements, like the 8 electrons. We then go into the fourth shell with the 4s, then come back to fill the 3d, and then move on to the 4p. So that layer contains 18 electrons, like we have 18 boxes in the periodic table. So the shape of the table is telling us about the electrons and which shell they're going into for the most part. But even the blocks of the table are telling us which kind of subshell the electrons are going into. Now we have to use a bit of artistic merit here and imagine helium on the left next to hydrogen. But if we do that, it gives us 1, 2 boxes on the left each time in each row, like the 2 electrons which are needed to fill a S subshell. made up of just one orbital. And then as we count boxes in that middle transition block, that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 boxes each time, just as there are 10 electrons in a d subshell. And with the right-hand block, if helium is moved across, 1, 2, 3, 4, 5, 6 boxes each time, just as there are 6 electrons going into a p subshell. So the shape of the table is really mimicking which shell and subshells the electrons are going into. The only two caveats to this, of course, are one, as we mentioned, we have to imagine that helium is on the left-hand side next to hydrogen. Okay, so it's not there anymore. And when we're looking for the shell number of the D subshell we're filling, subtract 1 from the row number to get the subshell number for the D subshell. So while we move along in the fourth row of the table, we'll be talking about the 4s, and we're talking about the 4p on the right-hand side. It's only the 3D subshell. If we move to the, say, the 6th shell, we're talking about the 6s subshell. We're talking about the 6p, but we're talking about the 5D subshell. The S and the P always stay in tune with the row number, the period, but the D subshell is always -1. As long as we remember these two caveats, we can always build a electron configuration, that zip code, for elements in the table with their electrons. Let's look at some examples and show that to be true. So let's do argon, which we've already done the block diagram for. And let's remind ourselves of where argon is in the table. There he is at the end of the third row of the table. And so as we count boxes, hydrogen and helium on the left-hand side, like 2 electrons going into the 1s subshell. So we get 1s2, then a little comma as we move to the next subshell. And for argon, after hydrogen and helium, we then have lithium and beryllium, which is back on the left in the second row. So we're talking about the second shell, the 2s subshell. Just my page moving on me. Can I get it back? I guess that's close enough. With the lithium and beryllium, so 2s2, pull up the periodic table again. Next, after lithium and beryllium, we're on the right-hand block and we count boron all the way through to neon. 6 boxes in the right-hand block in the second row. That's our 6 electrons going into the first example of a 2p subshell. Because it's in the second row, it's the 2p with 6 electrons. That takes us to the end of the second row. So looking at the table again, into the third row with sodium and magnesium on the left, which we said was the S block. And so we do 3s2. And then finally, as we reach argon, look at our periodic table one last time. So from magnesium, we count aluminium or aluminum for our American friends, silicon, phosphorus, sulfur, chlorine. Finally, our target, argon. 6 more boxes on the right-hand side of the third row. So we now finish with 3p6. And we did that without memorizing anything. We just followed the shape of the periodic table. The left-hand block representing the S subshell, the right-hand block representing the P, and that middle transition block representing a D subshell. Let's look at some more. I wonder if I can get the periodic table on the page at the same time here. Might work. Yep, looks like it is. So for magnesium, we look for magnesium on the periodic table. Let me switch to red just for a bit better color this time. So there's the magnesium there. But we start with hydrogen each time. And again, we imagine that helium is actually on the left-hand side. So 1, 2, hydrogen, helium to give us 1s2, lithium, beryllium to give us 2s2, boron all the way through to neon to give us 2p6, and then sodium and magnesium to give us 3s2, the complete electron configuration. As we switch to the next one, now it's sulfur, the target. Again, starting in the top left corner, hydrogen and helium to give us 1s2, lithium and beryllium to give us 2s2, boron through to neon to give us 2p6, sodium and magnesium 3s2, then aluminium, silicon, phosphorus, sulfur, 4 boxes for 3p4. Then looking at calcium for our next target. So hydrogen and helium again, 1s2, lithium and beryllium for 2s2, then boron to neon for 2p6, sodium magnesium for 3s2, aluminium to argon for 3p6, then finally in the fourth row on the left hand side, potassium and calcium for 4s2 as we finish up with calcium. Finally iron, so this is our new target, starting with hydrogen again. We fill up like we did before for calcium, so we're up to 4s2 at this point, just to save a bit of time. I think we're getting used to it now. And then it goes beyond calcium's configuration by having 1, 2, 3, 4, 5, 6 boxes in this transition block. That's a D subshell, but it's 1 less than the actual row number, so it's 3d6. Okay. Now, the only problem with these electron configurations is that if we move further down the table, we can get some very long-winded configurations when we start looking at elements in the 5th, 6th, or 7th row. That's a lot of configuration to write. And so we'd like to write the shorthand configuration for the element. And that's what we'll look at in a couple of minutes, because I forgot I've got some extra examples to do. So if you're looking at a periodic, well, let's bring it up. I'll bring it up again and just let you work it out from the position. Looking at helium, that's simple enough. 2 boxes, so 1s2 for the configuration. From carbon's position, that'd be 1s2, 2s2, 2p2 for carbon. For sodium, at the beginning of the third row, 1s2, 2s2, 2p6, 3s1. And finally phosphorus, a little bit further along in the third row. So 1s2, 2s2, 2p6, 3s2, 3p3. for phosphorus. So again, if we're looking at something like cesium or barium or thallium, lead, that's quite far down in the table, and therefore there'd be a lot of subshells to write out. And so we can actually simplify it because chemical reactions show us that all of the change in an atom in terms of its electrons, it happens solely in the outer shell of the atom, what we sometimes refer to as the valence shell. And so we sometimes just emphasize the electrons in that outer shell, that valence shell of the atom, by using the noble gas at the end of the previous row. Again, let's bring up the periodic table side by side to look at this. Whoop, why did that trigger? Excuse me, I've just got a piece of software which is trying to trigger. Is that it? Has it gone away? Hopefully. So if we look at magnesium, we wrote it as 1s2, 2s2, 2p6, 3s2. That's a bit long-winded. And so there's software appearing here, so give me a second. Just clicked on something by mistake. And so where are we at? Where are we? Magnesium. There we are. So with magnesium, when chemicals and molecules react, it's just that outer layer which interacts with its neighbor through collisions. And we're really just talking about the electrons in the outer shell. They're the ones which are meeting the collision head on. And so anything from a previous shell is normally untouched by a chemical reaction. It's just the outer layer of electrons, which is what we sometimes call the valence electrons. Valence shell, valence electrons, just the electrons in that very top shell. They're the electrons furthest from the nucleus, and therefore the ones which feel the weakest attraction to the protons in the nucleus. So for magnesium, we can summarize that it has two shells complete, just like neon. And we'll use that symbol in parentheses and then emphasize just the valence electrons for magnesium by writing the 3s2. Likewise with sulfur, there's sulfur there. It's got two shells complete like neon. So we use the chemical symbol for neon in square parentheses and then just write out that valence shell configuration, the sodium and the magnesium for 3s2, and then the aluminum, silicon, phosphorus, sulfur for 3p4. Whatever the element is, like say selenium, back up to the end of the previous row, use the chemical symbol for that noble gas, and then just write the valence shell configuration. If we look at some of the others we've had, adjust my page and bring up the periodic table again. So for calcium, we've gone into the fourth row of the table, into the fourth shell. We can back up to the end of the third shell and use argon in square parentheses to allude to those three shells which are complete, and then just write 4s2 for the calcium along with the symbol for argon. With iron, which is in the middle of the table, of course, again back up to the end of the previous row where we find argon once more. So we can use argon and then write 4s2 as we count potassium and calcium, and then 3d6 as we count scandium, titanium, vanadium, chromium, manganese, iron. 6 boxes, 6 electrons. But remember the D subshell is always one behind the row number that it's attached to. So that's a simpler way to write electron configurations. Emphasize the completed layers by using the element at the end of that row and just write the valence shell configuration. Just watch out for an element which is a noble gas like argon. We can't just write argon in square parentheses because we haven't included the valence electrons. So just like the other elements, we back up to the end of the previous row where we find neon at the end of the second row. And so then we can write the valence electrons for argon as 3s2, 3p6. Let's try some more, writing the shorthand configuration for these elements. And let me take a break to get a drink. And you can pause the video at this point and try and come up with the answers for yourself. All right, so let's look at these elements and their electron configurations. So if we look at the position of nitrogen in the table, it's in the second row. So we can back up to the end of the first row and say that its configuration is like helium, putting the helium in square parentheses, of course. Because that's why my eyesight's all blurry, because I don't have my reading glasses on. Like helium, but then goes beyond helium with 2s2, 2p3. Chlorine, from its position in the table, we back up to the end of the second row and we'll use neon in square parentheses to allude to two shells complete like neon. And then we can say 3s2, 3p5. With vanadium, there's vanadium in the fourth row of the table. So we back up to the end of the third row with argon. So 3 layers of electrons complete like argon. Then 4s2, 3d3. Remember the D subshell is one behind the row count. Then bromine, almost at the end of the fourth row. So we're using argon once more. And we can say 4s2, 3d10, 4p5. All right. So moving on, finishing up the chapter, we've got just a couple of questions alluding to those trends that we had talked about earlier before we looked at electron configurations, the changing size of atoms as we moved around the periodic table, and the changing ability for atoms to attract electrons, what we called electronegativity. Thanks to the students who pointed out for my campus lecture this morning, I'd got myself a bit backward. I was talking about atom size in class when I should have been talking about the attraction for electrons. So this time I am going to talk about attraction for electrons, as it says in the question. So remember, when it came to attraction for electrons, we said that, so let me draw on a really badly drawn a periodic table apparently. So like that kind of. What a terrible artist I was. I used to be good. I was good as a kid, but that was a long time ago. We said for ability to attract electrons, that ability increased as we moved to the right, and that attraction for electrons increased as we moved towards the top. And as we look at the elements listed here, calcium, bromine, iron, manganese, we find these elements all in the fourth row of the table, fourth period. Let me just prove that. So here we are, see the calcium, manganese, what else we got? Iron right next door, and the bromine. And so if they're better at attracting electrons as we move to the right, then the best of the best must be the bromine. It's the furthest element on the right-hand side. But why is it the best? Why does it help to attract electrons the further to the right you are? Well, the one thing that changes as we move to the right is the atomic number, the number of protons. And so atoms further to the right have more protons, and that's what the electrons are attracted to, the protons in the nucleus. So elements or atoms with more protons should be better at attracting electrons. So that's why a bromine wins. Let's look at 2.7 over the page. Let me just try and clear things up here. We'll keep that stuff. So, let's see. Move the page up. So now looking at 2.7. Now which elements would you predict to be, or which element would you predict to be the best at attracting electrons? And now we have calcium, strontium, magnesium, barium. All elements in the same group of the table, group 2. Calcium, barium, strontium, and magnesium. And we say that the ability to attract electrons increases as we move towards the top of the group. We should make our winner magnesium. We haven't included beryllium in this example, so you must be talking about magnesium. Why is the magnesium better? Well, as we move up the group, the number of protons diminishes. That doesn't seem good. That's a contradiction to what we had talked about in the previous question when we came up with bromine for the answer. Although the number of protons is decreasing, there's a much more significant change for the atoms of these elements as we move up the group. And that's the stripping away of layers, the stripping away of shells. Remember, every row of the table is like another shell. So with fewer shells, the elements at the top are relatively smaller atoms. And so that close proximity, because of the small size of the atom, means that the electrons are closer to the nucleus, even though we have less protons in that nucleus. So a relatively small atom, like magnesium, with a small distance from nucleus to that last electron, is better for attracting electrons than a relatively big element like barium, with a much larger distance, much larger radius from the nucleus to the edge, much larger atoms. It might have more protons, but if the electrons are sufficiently far away from the protons, the electron attraction to protons diminishes, just like holding a magnet further away from a piece of metal. That attraction diminishes over distance. So attraction increases to the right because of more protons, and attraction increases towards the top because of fewer shells. Now, when you're faced with a question like this, always think about, are we talking about elements in the same period or elements in the same row? If we're talking about elements in the same, sorry, I said period and row, the same period / row, or elements in the same group, up and down, columns. If we're talking about elements in the same period, i.e. the same row, left to right, then it's the number of protons which is important. If we're talking about elements in the same group, up and down, we're talking about the number of shells, which is important. So the non-metals are really good at attracting electrons, and the metals to the left and to the bottom are really rubbish at attracting electrons. That's basically what we're saying. Next two examples, which I effectively went over in class today using the wrong questions. So now we're thinking about which atoms are the biggest. And we are looking at elements now: boron, carbon, lithium, oxygen, elements in the same period once more. We can confirm that. There's our carbon, there's our boron, there's our oxygen, there's our lithium. And again, when we're looking at the periodic table and those trends from left to right, we've already established and said that when it comes to elements in the same row, same period, the size of the atom increases as we move in the other direction. And we had said from the previous questions when talking about the attraction for electrons, it was about the number of protons. And that's still true when we're considering atom size. So looking at, for example, boron compared to, say, what's on the other side? Oh, actually not boron. That's not our best example. Lithium's our best example. Excuse me, I've had too much sugar. Lithium, which is the one furthest to the left, and then furthest on the right is oxygen. It's really between these two. We know that it's going to be lithium which is the winner because it's further to the left. That was a basic analysis before we looked at electron configurations on Wednesday. But why is it the winner? We are saying that the number of protons decreases as we move to the left. So why does that help? Well, remember, for the size of the atom, it's about the distance from the nucleus to that last electron. And the distance influences the amount of attraction between the protons and the electrons. But if the number of protons decreases as we move to the left, with less protons, that electron feels less attraction. And so like a satellite with less gravitational pull from the planet, if gravity weakens, it's almost as if the electron suddenly is on a longer leash. It can drift out further from the nucleus, drift out further from the surface of the planet in the case of a satellite, and so that atom size gets bigger if there's less protons. It's not about the number of shells, because moving across the row, that period, we have got the same number of total shells each time. So elements to the left of the row are the bigger atoms because there's less protons. So there's less attraction to the electrons and protons. Last one, looking at fluorine, chlorine, bromine, iodine, and now looking for the biggest atoms. Again, as we look at our sketch of the periodic table, looking at atom size increases to the left, but it also increases as we move down towards the bottom. Why should it increase as we move to the bottom if there are increasing numbers of protons? Again, it's not about protons as we move down and up the group, it's about the number of shells. And an atom with more shells is just physically bigger. We're adding on layers, like layers of onion skin. And so with more shells, we've got a physically bigger atom. And that's it for size of atom and the comparative electronegativity. I'm going to jump some of these questions here for a second, just to do a summary of this, which I have on a later page. There we go, our main summary. So when we're looking at periodic trends, ask yourself, are we comparing elements in the same period from left to right or row, or are we comparing elements in the same group, columns from top to bottom? If it's about elements in the same period, then it's about the number of protons. If we're talking about atom size, it helps if we've got less protons. If it's about attracting electrons, then it helps to have more protons. That's why the atoms on the right are smaller. More protons, not only is the atom doing a better job of attracting its own electrons to make the atom smaller, but it's attracting electrons from other atoms. So left to right, the period is about the number of protons. You just have to figure out whether having more protons helps by moving to the right, or less protons helps by moving to the left. When we're looking at elements in the same group up and down, it's about the number of shells. It makes the atom bigger when we move down the group because we've got more shells, but it makes the atom better at attracting electrons if we remove the shells, and therefore the atom is smaller and the electrons are physically closer to the nucleus. That makes for better attraction. So this is a tricky one, but break it down into those component parts. Is it a group or period? So is it about shells or is it about protons? And does it help to have more protons and shells or less protons and shells? That should help you work your way through the answer. And finally, those last couple of questions, looking for the electron count. How many electrons does calcium have in its outer shell? That's just a case of looking at the periodic table, as I've said before. So for calcium, it's the second element in the fourth row. It has 2 electrons in its outer valence shell. The number of boxes you count in the row normally tells you the number of electrons. Just watch out for an element like vanadium in the table, because of course, although we initially put electrons in the 4s, we then switch to putting electrons in the 3d, 1, 2, 3. The configuration of 4s, 3d, 3. The fourth shell is the outermost shell. That is a valence shell, so we're only counting electrons going into the valence shell. So that would be 2 electrons as well for vanadium. If the question was about something like germanium over here, it'd be 1, 2 electrons in its 4s, then 10 electrons in the 3d, and then back to the 4p, 1, 2. So that would be 1, 2, 3, 4 electrons in its outer valence shell. Watch out for that D block. And then the last one, the number of unpaired electrons in an atom of iron. Well, there's iron there, element 26. And we can build up a block diagram for iron and its shells to make that apparent. Let me just try and clear some space here for myself. I'm going to try and move myself up the page just to clear some space. So if we draw the block diagram for the order that the subshells appear using the periodic table, I've got the 1s subshell, then the 2s, followed by the 2p, drawn very badly, I admit, and then the 3s subshell, there's a 3p, then, can I fit it in? The 4s, drawn very badly. And of course, now we have the D subshell. 1, 2, 3, 4, 5. Oh, made that last one a little bit big, but never mind. And then higher in energy, the 4p after the 3d. So element 26, iron, we've got 26 electrons to account for. And following our three rules, Aufbau principle, the lowest energy shells and subshells filled first. Then Pauli exclusion principle, a maximum of 2 electrons, so we have to move up to the next subshell. Whoops. Then Hund's rule, they don't pair up until there's no other space. Another 2 in there. Fill up to 3p to take us up to 18, 19, 20, 21, 22, 23, 24, 25, 26. And so as we do the block diagram, we can see the space for another 1, 2, 3, 4 electrons, giving us 4 unpaired electrons. Okay, one last question, I believe. So there's a scan of a patient's thyroid gland. How was that scan made? And what would be the diagnosis for the patient? I think my cat's behind me, isn't she? Yes, she is, where she usually sits. So we said that you need to give the patient a sample of sodium iodide, but specifically a radioactive sample of sodium iodide. The iodine collects in the thyroid gland where it's stored to be used to make the hormone thyroxine. And so if you give the patient a radioactive sample, that iodine will emit radiation from the thyroid gland, and that concentration of iodine shows up as an intensity of color. The more hot the color, the greater the amount of iodine. The more cold and blue, the less iodine. So comparing the two glands, it seems to be a lot cooler on this side here, suggesting a low concentration of iodine, which could mean that the cells are not working properly, maybe even something as serious as cancer. Okay, that takes us to the end of the chapter. And I hope that helped. Again, we'll continue with this in the weeks to come. I'll do online videos on Monday, Wednesday, and Friday, mirroring the appearance of Section 1 on campus on Mondays, Wednesdays, and Fridays, so to speak. Lecture on Monday is probably going to be late in the day, or at least after 6. Wednesday lecture, I'm actually recording what I do at home on Wednesday morning, so that'll be a morning release, or lunchtime, I guess, because it's 11 till 12. And then Friday will be a evening release once again. I might toy with the idea of setting up a regular time for the Monday and Friday, and then put up a Zoom link in case anybody wants to join me for those meetings, maybe 8 o'clock on Monday and Friday night. You don't have to, but if people would like to join me, and it then gives them a chance to ask questions, maybe we'll treat it like that. And of course, Wednesday will always be at 11 a.m. where people can join me as well. Okay, hope that helped. Stay safe, wash your hands, wear that mask.